So if I keep on following, what we have is we have expectation of, let's square out this thing. So the half is going to be equal to a fourth, okay? And we are going to have x1 minus e x1 squared plus, well, plus 2 times x1 minus e x1 x2 minus e x2, okay, plus x2 minus e x2 squared, and that's my expectation, and I have a square root here. What's important is that this term is going to be gone. The reason for that is this is independent from this, and therefore the expectation of the product is equal to the product of the expectation, and the expectation of the first term is actually 0 because I have expectation of x1 minus expectation of x1, right? So they cancel out. The expectation of the second term is also 0 because I have expectation of x2 minus expectation of x2, so that also cancels out. So the result is that I can safely remove the second term, and what I get out is going to be expectation of essentially a fourth, which I should really move out of the expectation. So let's see, let's move the fourth out of the expectation. And inside the expectation, I have x1 minus e x1 squared, right? And plus x2 minus e x2 squared, okay, to the square root. And the expectation of the sum is equal to the sum of the expectation. So I have a fourth times really twice the expectation of x minus expectation of x. Remember, this is x1 and x2 are identically distributed, so the expectation of the same function of them are going to be the same. So if I keep going, the fourth cancels with the 2, so I get half here, and half taken square root is 1 over square root of 2 times expectation of x minus expectation of x, which is the standard deviation, right? So this is the standard deviation. So which means by adding 2 samples as opposed to 1 sample, I have reduced the standard error by a factor of 1 over square root of 2. This analysis can be continued with however many samples you want, right? If I use 3 samples, the standard error is going to be reduced by square root of 3. If I use 100 samples, the standard error is going to be reduced by a factor of square root of 100, which is 10. So this is really a lead to the following formula. So the standard error for an estimator, that is 1 over n, the summation I goes from 1 to n, xi, where xi are independent, identically distributed estimators, is going to be 1 over square root of n times the standard error of just taking one of them. All right. So this is going to lead to a satisfactory answer to the question, how many samples do I need to use? It depends on how much error you are looking for. Remember our single sample, right? In our particular case, the standard error of a single estimate is equal to p a square root of p times 1 minus p, right? So when x is a 0, 1 random variable, being 1 with probability p and 0 with probability 1 minus p. So the standard error of n samples is going to be 1 over square root of n, or if I just put everything in, it's square root of p times 1 minus p divided by n. Okay, so it depends how accurate of a result do you want. If you want very accurate results, if I want a precision within, let's say, 0.1%. So let's say, let's go back to our MATLAB example, right? So we know with a single sample, we roughly get a standard error of 8%. If I want a 0.1%, that means I need to reduce my error by a factor of something about 100, right? Okay, so if I need to reduce my error by a factor of 100, how big of n do I need to use? What n would lead me to a reduction of the error by a factor of 100?
100 squared.
100 squared, or 10,000 exactly. Very good.